All right, I think we can get started. So hello everyone, my name is Guoning Chen. So welcome to the IEEE workshops on topological data analysis and visualization, or TopoInVis. Okay, I know this is not how I envision how we would get together, but in ideal scenario, I would like or love to meet everybody in person. But considering the recent back-to-back hurricanes, IEEE made the hard decision to move the conference online. And I know a lot of people, spent the past 2 years working really hard to bring the conference to Tampa, like, the General Chair Paul, who was also the past chair of TopoInVis, worked really hard. But I think this is the right decision, given the current ongoing events. And then we certainly do not want to disrupt the people's effort there to recover, and we want to give them some time to heal. We can find other ways to help them, but right now our thoughts are with those, got impacted. Moving to the virtual setup in such a short amount of time is not easy. So I'd like to thank the IEEE tech team to be able to pull this off in such short amount of time. And also, I want to thank the whole community to provide your support to make this happen. And I understand, or we understand, moving things to virtual can bring some challenges, like dealing with different time zones and possibly technical difficulty. And I appreciate you joining us from different time zones, overcoming all those challenges today. And we try our best to make it a smooth experience as possible. Thank you very much. Right, now back to the workshop. So this is TopoInVis workshop, and it provides a premium platform for the researchers as well as practitioners to share their latest accomplishments on techniques and applications on topological data analysis and visualization. And topology-based methods are a line of techniques aimed to extract the structural information of the data. And many of them may call it the shape of the data. Right? The structural information usually peel out the non-essential information of the data and allows the users to focus on the essential information. And essential means that usually you can, derive and mostly approximate the other information from it. Like they are usually built on solid mathematical foundations. Many of them have provable guarantee, and many of them do not or have little needs on parameter tuning in order to get the result. This is very different from other, threshold-based methods. And it provides, a mathematically corrective, structurally consistent representation of the data, right? This is very good to handle very large-scale complex data with a lot of details that other methods may miss, right? Because of all those advantages, topological methods have found a lot of applications in different fields, and it's still growing. All right. So I took the liberty and tried to, provide the roadmap of topology-based methods in the visualization communities. So this is not necessarily precise, but I try my best, right? I believe you all agree the topology-based methods in the visualization communities start with scalar field topology, right, in the early 80s. And then following that, we have the introduction of vector fields and is handling very simple data sets in low dimension space, like 2D space. And when things moving toward to practical setup that we need to deal with complex data, other techniques need to be introduced, like topological simplification, right, to provide level of detail representation of the data, and topology for high dimensional space, like 3D vector and tensor field topology. And time-dependent topology also introduced about the same time in the early 20s. So I did my PhD focusing on vector field topology in 2004. And then things just keep evolving from that point and getting bigger and more challenging to handle more challenging situations. Like we start seeing topology with uncertainty and topology for ensemble data, and then topology jumping out of traditional scientific data territory and trying to handle high-dimensional data in abstract space. And then now topology trying to handle the challenge of multi-fuse data analysis, addressing graphs and hypergraphs. And then we start seeing topology being applied to machine learning and deep neural network problem. So in the meantime, we also see topology being applied successfully in various applications, ranging from scientific applications, engineering, biology applications, medicines, and social science. So things are still, moving forward, very, very, active fields, and I think it's a good time to join the field. All right, so let's, take a look at a little bit about the history of TopoInVis workshop. So it started in, 2005, and TopoInVis was about 15 years. The workshop was held in different countries every other year, right? And then the attendees during that time were mostly researchers from the visualization communities. And things were well until the pandemic hit. And after pandemic, the steering committee of the workshop decided to co-locate the workshop with IEEE VIS. So starting with the VIS 2022 in Oklahoma, that's our first, edition of co-located events with IEEE VIS, followed by last year's workshop in Melbourne and this year's. Right, the goal of moving IEEE, the TopoInVis workshop with IEEE is to bring the topology-based method to a bigger audience, an audience that should include not just researchers from the visualization community, but also practitioners and researchers from application fields. And I believe in the last two editions, we are partially achieving that goals with attendees, having more than 80 attendees from visualization community and other application fields. All right, so this is a slogan I borrow from a truck that I saw. Be a part of something as big as you can fill out the dots. All right. Okay, so this year I'm fortunate with fortunate working with an amazing team while organizing the workshops. So DVR and I are serving as the overall co-chairs, overseeing different administrative aspects of the workshops, including some paperwork that was required by IEEE, and identifying and inviting the keynote speaker and synchronizing, collaborating with other chairs for other aspects of the workshop. And Federico and Red served as the paper co-chair and organizing, helping up setting up the IPC, organizing the paper reviews. And I want to emphasize, Federico, during when things are dynamic and uncertain, Federico took the lead and send out email and keep everybody in the loop with the timely informations. So to prevent things falling apart, which is, I appreciate that. And finally, we have Link, who actually, help us post the most up-to-date information to our webpage to keep everybody, updated. So I would like to thank every one of you here for making this workshop happen. Thank you very much. All right, now speaking about the technical paper selections. So, and then the paper chair, as mentioned, Federico and Red helped us set up the IPC, which consists of 22 members. And and each submission was reviewed by 3 IPC members. Among 10 submissions, 6 were accepted as full-length paper. And then among the 6, 1 selected as best paper, which DVR will introduce next. And for the substantive paper, they will receive 10 minutes presentation plus a 2-minute Q&A in the paper sections. And this year, we also accept posters. So we extended the invitation to 2 rejected papers as a poster presentation, and they accepted that. And the posters will be, joined with the poster for the main event of IEEE. And on top of that, during today's workshop, they also get to have a lightning talk. So for 3 minutes presentation and 2-minute Q&A. All right, so this is today's agenda. I try to, speed things up a little bit. And following the opening mark, we'll have the keynote presentation by Professor Bielnik. And after that, we move toward to best paper presentation. And then we have a break, 25 minutes break. When we return, we will have the paper section with 5 remaining papers hosted by Holger and a poster section hosted by Federico. And if everything goes smoothly, hopefully we will wrap things up at 3. All right, before we wrap up to the openings, so here I would like to thank everybody's watching us here in the room and outside there. And specifically, I want to thank the IEEE Viz co-organizer and special shout out to tech team. And thank everybody's effort and students volunteer to help, with any technical issues. So, and with that, I close my, opening, and without further delays, I move to today's keynote presentation. So today, we're happy to have Professor's keynote presentation about his work on topological data analysis and visualization in biological imaging and videos. So Dr. Pionek received his PhD at the University of Toronto in 2003 and was a postdoc at EPFL 2003 to 2005. And he joined the Cleveland State University in 2005 to 2015. And since 2015, he has been at the University of Florida. And he founded the Applied Algebraic Topology Research Network. And since then, he has served as on the advisory board. So Dr. Bielnik's research focused on developing new tools for summarizing and visualizing large, complex, high-dimensional data from algebraic topology and machine learning. So I think he will touch based on some of those, interesting ideas in today's keynote presentations. So with that, the stage is yours. Thank you.
Thank you. Thank you very much for screen so that I can share mine.
There you go.
So thank you for the introduction, and thank you for the invitation to speak here today. Please, reason unable to use your audio, please use the chat your question during my talk. So a very brief outline. I'll start with an introduction or a review of topological data analysis, and then I'm going to share 3 projects with you that I'm excited to talk about and using topological data analysis for visualizing and understanding various biological data. All right, so what are we interested in doing in TDA? We're interested in analyzing data with a rich geometric and topological structure. So we're particularly interested in data where the geometry is somehow crucial for both crucial for understanding the data and is sufficiently complicated that standard methods don't do as well of it. So here's some examples, and of course, I think once you start thinking about TDA and looking at data, you realize that kind of data for which it can be used is ubiquitous. But of course, the note is that maybe most data is just linear, and we should just be using ordinary statistics or something to do it. All right, so what can we measure in topological data analysis? the basic idea is to capture somehow the shape of the data, and very, very classical invariants going back over 100 years are the Betty numbers. So here we have a torus on the left, the surface of a donut. It has one connected component. That's the 0th Betty number starting at 0. And then if we go up kind of one level, we get the first Betty number. We have two non-trivial cycles or two loops on the surface of the donut that are not contractible. Going up one other level, we have the second Betty number. There's one void that's inside the torus. And then since this is somehow a two-dimensional object, there aren't any higher Betty numbers, but these can also be computed. Now, around 100 years ago, Emmy Noether realized that these Betty numbers were really numbers associated with algebraic constructions. And this is coming from homology, and this is somehow the main technical tool of TDA. And the most common way in which it is computed in the computational setting is we have homology of a simplicial complex. So this is a combinatorial object consisting of vertices, edges,
5 very interesting papers. The first paper is called Critical Point Extraction from Multivariate Functional Approximations. The authors are Guankun Ma, David Lenz, Tom Peterka, Han-Ki Gu, and Bei Wang. And Guankun is going to give the presentation. Let's go, let's share the screen, and let's start.
Okay, everyone, can you see my screen?
Yes, perfect.
Okay, thank you. So hi, everyone. My name is Guanqun, and thank you for coming to my talk. Advances in HPC require new ways to represent large-scale scientific data, support data storage, transfers, and analysis. There has been a growing interest in replacing discrete data with continuous representations to enhance scientific workflows. Examples of continuous representations include functional models such as MFA and implicit neural networks. Among the functional models, MFA, or multivariate functional approximation, has recently emerged as a new continuous meshless representation of discrete data. An unexplored area of research is to utilize continuous implicit models such as MFA for topological data analysis and visualization. A fundamental step to recovering topology from an MFA model is to extract its critical points. The main contribution of our work is that we provide the first critical point extraction method for MFA models without discretization or resampling. And our work is the first step toward enabling continuous implicit models, such as MFA, to support topological data analysis at scale. First, what is an MFA model? MFA is an implicit meshless data representation. It uses a piecewise polynomial function to represent the data. We can query function values or derivatives anywhere in the domain. MFA consumes less space compared with the discrete data. However, as mentioned before, the topological features of MFA haven't been explored previously. Let's explain MFA a little bit more. Here is an example of a 1D MFA using B-splines. The data is represented by the blue curve, which comes from the B-splines, and the points from P0 to P10 are the control points that control the behavior of the blue curve. We use the horizontal green bar to represent the entire domain. We divide the domain into pieces called spans. Now, the blue curve is also divided into pieces, and there is one piece of the blue curve in each span, and we highlight it in red. Every red piece is a polynomial, and its values are controlled and bounded by the control points in red. Here is an example of a 2D MFA model using B-splines. The blue block in the bottom left corner represents a single span. The red points are the control points. Since we extracted critical points from an MFA model, what are critical points? They are the points with zero gradient. For 1D function, critical points include local minima and local maxima. And for 2D function, besides local minima and local maxima, critical points also include saddle points. Critical points are the simplest examples of topological features. Our framework that extracts critical points from MFA is called CP-MFA. First, we derive the control points of first derivatives. Second, based on these control points, we skip spans where the first derivative do not pass zero. This is called span skipping. And finally, we use Newton's method in each span to extract critical points. Here is a 1D example. The blue curve is the MFA function. The orange points are the control points. An MFA model enjoys a nice property. The first derivative of an MFA function is also an MFA function. Here, the first derivative of an MFA function is also shown in blue with its control points in orange. To find the critical points of an MFA function is equivalent to finding the zeros of its first derivative function. In the red box, all control points have values above zero. This implies that there are no critical points in these spans. Therefore, we can skip these spans. And finally, for each of the remaining span, it's a polynomial function. So we can use Newton's method to extract all critical points. And we can see these two red points corresponds to two locations with zero first derivatives. And the left point corresponds to a local maximum. And the red points corresponds to a local minimum. We now give a few example results. And please refer to our paper for complete results. This is an example of a synthetic function. We use MFA to fit a discrete data set, form this function, and extract its critical points. All the red points are the critical points we extracted from the MFA model. We locate all 900 critical points with 100% accuracy, and our result is consistent with the analytical result. And we now demonstrate our result across scientific data sets. We evaluate the output of our framework against those obtained by applying TDK to an MFA model. TDK assumes that the input data is a piecewise linear scalar field and extract its critical points. We aim to demonstrate that the critical point extracted by our approach align well with those extracted by TDK. Since an MFA model is continuous, so we sample a discrete data set from the MFA model and then apply TDK. In other words, the result of TDK serves as a reference, not a ground truth. This example is from a 2D CSM dataset, and it is a global climate dataset. Our analysis focuses on the FLDSC variable, which represents the clear sky downwelling long wave flux on the surface. Here, pink points are the critical points extracted from our method. Purple points are critical points extracted from TDK. Yellow points are the critical points that are perfectly aligned between the two methods. The zoom-in view shows majority alignment with a few disagreement between the two methods. However, after we upsampled the dataset, we can see increasingly alignment between critical points extracted from the data. we show an example of a 3D QMC dataset that comes from the calculations of electronic structures. Again, the critical points extracted from our approach are shown to be mostly aligned with those extracted by TDK. And to summarize, we provide the first critical point extraction method from MFA models. And our work is the first step toward enabling continuous implicit models such as MFA to support topological data analysis at scale. And for future work, we will focus on extracting more complex topological features from MFA, such as contours and Morse complexes. And finally, we would like to thank DOE and NSF for supporting our work. Thank you.
Thank you very much for this very nice presentation. The floor is open to question, and floor means Slido or Discord. I do not see any questions yet, so let me start with the questions. Do you have any guarantees that you find all critical points?
Oh yeah, I think we mentioned this in the paper because of the I think because of the nature property of Newton's method. Currently, we cannot guarantee because it depends on the initial points of Newton's method. And but I think because you know, like for MFA, for every span it's a polynomial function, and we know its degree. So actually we know how many critical points at most in every span. And I think in the future, and we mentioned like we want to use something like laser curves to improve our Newton's method. I think that can have a guarantee to find all critical points.
Mm-hmm. Okay, that brings me straight to the next question. You say you know how many critical points can maximal be in one span.
Yeah.
So how many points can be in a span?
Yeah,
what
like
is this number, this magic number?
For example, in one span, it's a polynomial function. So we know its degree. For example, it's degree 3 or degree 4, and then we know, like for example, for a 2D in a 2D domain, it will be the degree number. Like we know, like for a 2D function, for example, for a 1D function for degree 2, it will have at most one root.
Mm-hmm.
For a degree 3 function, it will have at most two. For a function of degree 2, it will have at most two roots, and for degree 3 function, to have at most 3 degrees. So for n dimension, to have degree to the power of n roots at most in one span.
Okay. There is another question in Slido. So this method is meshless, right? Does it mean that we can get away from needing a TET mesh or simplex mesh to extract topology?
Yeah. Yes, this model is continuous. So all of our operations are based on this, are in this continuous domain.
Okay. There are more questions. Are all MFA Morse functions?
Yeah, I think like for example, for most functions, we require for two adjacent points, their function values are not equal. But actually for real data, we cannot guarantee this. So I think we also mentioned this in the limitation, like in the real data, we cannot guarantee all function values all adjacent points have equal function values.
All right. Another question, which simulation codes are run with the MFA model?
Which simulation code?
Which simulation codes are run with the MFA model? So the question is probably how to get this MFA model. What kind of simulation is behind?
Yeah, like for MFA itself, this code is already open sourced.
Mm-hmm.
to get the MFA model. But for our part, like to extract the critical point, we haven't open sourced this kind of this part of code.
All right. Last question before we have to move ahead. Can we tell the type of critical point from the extracted points using your method?
Yes, we can. Because we know like for the type of critical point, we can decide it based on the hashing point of based on the hashing matrix. And because this is a continuous matrix, this is a continuous function, and we already know its hashing matrix, so we can directly decide the critical point types.
All right. Thank you very much. I think this answers hopefully everything. And thanks again for this nice presentation and answering all our questions.
Thank you.
And we come straight to the second presentation. The title is Topological Simplifications of Jacobi Sets for piecewise nearby where 2D scalar fields by adjustment of the underlying data. Longest title today. Your authors are Felix Reit, Gerig Scheuermann, and Christian Heine. And the long title gave us time enough to set up everything. And we can just start now. Felix, go ahead.
Yeah, thank you. Yeah, thank you for the introduction. My name is Felix, and I will tell you something about our motivation and the idea in the first part of this talk. Following that, I will short present our results. So scalar fields are often used to visualize interesting quantities such as temperature or high about sea level. This can be analyzed using topology methods, for example, by interpreting the scalar values as a high over the observation space. You can find extrema like minima or maxima. So from which contours can be derived? This data can be analyzed, for example, in a contour tree, but this can become very complex if the data is noisy. Therefore, there are different ways to simplify such data for scalar fields. The goal is not to lose important structures and still simplify the data. Let us now look at myriad scalar fields. Here we have a domain and a range of a function. With this, the data can be visualized and analyzed using continuous scatter plots in the range. Structures can be recognized where there is an increased density. The different densities divided the dataset into different regions. Here can be recognized by a black line, which also called Jacobi sets, which can become very complex, especially with noise. To simplify the Jacobi sets, there are already several approaches. Simplifies Jacobi set, but doesn't change the underlying data, which is useful for using the data set further. We therefore propose the approach that simplifies the Jacobi sets by simplifying the underlying data. To do this, we first calculate the Jacobi sets, create a neighborhood graph for the Jacobi sets, identify regions in the graph that should be removed, and remove these regions by collapsing the cells into degenerate cells until the regions in the neighborhood graph have been removed. We call this approach collapse algorithm. To calculate the Jacobi sets, we don't use the standard calculation, but a simple approach for 2D to split the field into positive, here red, or negative, here blue regions. The Jacobi is located in the boundary. The normal neighborhood graph is created in which each node corresponds to a region enclosed by a Jacobi set, and the edges correspond to their neighborhood. This region then contains cells whose orientation has the same side and are connected via a cell edge, are seen in this graph. We call this variant A and investigate what effect different variants have on the result of our algorithm. And variant B, in addition to the normal node definition, regions are connected if they are connected via a point and both have a negative sign, which leads to this graph. Variant C is like variant B, expected that here regions are connected whose sign is positive. In variant D, regions are combined if they are connected in a point and the majority of the neighborhood cells have the same sign. In this yellow point, 4 cells have a negative sign, so all blue regions are connected at this point. If the number of positive and negative cells is equal, then the area in the range is used. This is used for all points to generate the following graph. The neighborhood graphs become very complex, even with simple examples like this. To identify regions in this graph that should be removed, we consider three metrics as threshold: the cell regions area in the domain, the area in the range, and a hypervolume, which is a combination of the area in the domain and the range. We use the hypervolume in this example. The regions to be removed are marked in gray. And the area of the range is visualized by the saturation of the cells. The algorithm terminates as soon as there are only regions in the graphs that should not be removed or when the cells oscillate. In 2D, collapsing is complex and also depends on the neighborhood. We have therefore divided this into 4 cases. In the first case, if a cell is surrounded by cells that should not be removed, we collapse the cell to a point or a line. This is a degenerate cell. If there is a cell to be removed at an edge, we collapse the cell to a line by collapsing this edge. If there are cells to be removed on 2 edges, then we also collapse to a line by choosing the best variant. And if the cell is surrounded by cells to be removed, then we skip them in this step. In this way, we reduce regions starting from the edge. If this example, I will show you how to choose the best variant. If we want to remove this red cell, we have 4 possibilities to collapse. In the first variant, 2 cells are collapsed and 1 changed is signed. This is marked as the best variant. When we look at the second variant, where only 2 cells are collapsed, this variant therefore has prior changes in the neighborhood and is marked as the best. We look at the 2 other variants and don't see a better variant. So therefore, we stay with this variant and can remove the region. When visualizing the Jacobi sets of data set with degenerate cells, we observed that their visualization doesn't work in all cases. Cells that are degenerates are already assigned to positive or negative cells. In this example, always the negative ones. So we have adjusted the visualization algorithm to say degenerate cells are assigned to positive or negative according to the neighborhoods. Now it works very well for degenerate cells. In the results, we look at the effects of Jacobi set simplification of simple approach that change the underlying data, study the effects of the different neighborhood graphs on our algorithm, and then compare the best variant with the original data and the simple approach. Our first data set is the analytical cylinder flow, where the analysis the velocity component. To visualize a comparison of several moving filters in the loop subdivision with the original data shows that in the green region of interest, the Gaussian filter removes the Jacobi set best. In the brown region of interest, the loop subdivision is best because the large components remain here. And in the yellow region of interest, the loop subdivision is also resolved best, as the larger region is retained and is also better separated. When we comparison the different variants of our collapse algorithm, the algorithm are equal good in the green region of interest. In the brown region of interest, variant A is the best, and in the yellow region of interest, also variant A is the best. We therefore compare variant A with the original data in detail. So this shows that the data in all 3 regions can be simplified well, and that no unwanted changes occur in the remaining dataset. If we look at the comparative metrics, we see that the Jacobi sets are also very well simplified. When looking at the range for these 2 data, it can also be seen that the collapsing of the cells has no major influence on the appearance. However, when looking at the neighborhood graph, it can be seen that this can be greatly simplified and just the Jacobi set can be simplified accordingly. Now let's take a look at the tensor bar collection and take a closer look at two of them. We compare the original data with the loop subdivision and the collapse algorithm. For the first tensor bar, we can see that there is also a clear Jacobi set simplification. However, it can also be seen visually that the collapse algorithm has a problem with the symmetry of the very symmetrical data set. The comparative metrics also shows the effect on simplification and also show the problem of the loop subdivision with the more Jacobi set components and the higher length. For the second tensor bar, the collapse algorithm delivered a very good result, and even large unimportant regions are removed. To summarize, we have presented an algorithm for simplifying the Jacobi sets based on cell collapsing. We have adapted the visualization of Jacobi sets to count for degenerate cells. And we show the effect of smoothing, loop subdivision, and our collapse algorithm on Jacobi set simplification. The next steps are as followed. We want to automatically select the collapsing regions. We want to smooth the collapsed regions, and we want to adapt the algorithm to bivariate 3D data sets. Thanks for your attention.
Thank you very much for this nice presentation. Floor is open to questions. I don't see any questions yet, so let me start. Can you say something about the performance of your algorithm? Is it something that takes minutes, seconds, hours, what we've seen here?
The algorithm needs seconds
Okay.
to remove these elements. Yeah.
Okay. The other question, you said in future research something about we want to go to 3D. How complicated is it? Is it just a minor step, or would it be a completely different project story, whatever?
Yeah, it's a little bit complicated. The problem in 3D is that we not have only a triangle to simplify. We have a tetrahedra. So the options to collapse this is more difficult. We have a triangle, a line, a point, and on what position we change it. This is very complex. Another problem is when we have when we identify the regions we will collapse. This is not so easy in 3D. So this is more a major step in this point.
Yeah. Okay. There is a further question. Bai Wang is asking, is the complexity of the graph an indicator of the complexity of the underlying Jacobi set? Is there a correlation?
Yeah, I'm not sure to 100%, but yes, I think so. Yes, it's a correlation. Yeah. But
Okay.
when we have this complex graph on the one example, you have many problems when we have a cell and around is more than one cell. This is really in the problem when we have it noisy, since it's really complex. And you can see it in this problem. Yeah.
Okay. It seems to be the starting point of an interesting offline discussion. And okay, with this, thanks again for answering all our questions and the presentation, Felix. And we come straight to the third paper, which is called Revisiting Accurate Geometry for Morse-Smale Complexes. And this is pre-recorded. Son Letan, Michael Ankele, and Tino Weinkauf. And let's go with the presentation.
Hello, everyone. I'm Sean from KTH Sweden, and today I'm presenting our paper with Michael Ankele and Tino Weinkauf entitled Revisiting Accurate Geometry for Morse-Smale Complexes. So let's get started. Let's briefly recap what is a Morse-Smale complex. Given a scalar fields whose values are color-encoded, red is for higher values and blue is for lower values. The points where the gradient becomes zeros are called critical points. And in 2D cases, there are 3 types of critical points: minimum, saddle, and maximum, respectively. And integrating the streamlines starting at the saddle points in the direction of the eigenvector gives us the separatrices. The separatrices together with the critical points give us the Morse-Mel complex. In the traditional continuous setting, the Morse-Mel complex can be challenging to compute in practice. To overcome this problem, one can use discrete Morse theory, first introduced by Robin Foreman. This version of Morse theory aims to describe the concepts and the properties of the continuous Morse theory, but in a combinatorial manner. Instead of working with the continuous scalar fields, we are now working with functions whose values are placed at a component of a grid, so that there are grid vertices, grid edges, and grid cells. And instead of computing the gradient at every point on the domain, we now compute the matching arms to describe the discrete gradient fields. And they can be thought of as arrows linking the vertices to the edges and edges to the cells. We can see that there are unmatched components on the grid. They are called critical cells, and based on the type of component they will be matched accordingly. Vertices are called minima, edges are saddles, and cells are called maxima. Together with the gradient fields, we can create the discrete Morse-Mel complex, and we can see here they are almost identical. So, how to compute discrete Morse-Mel complex? For our intention, we consider different scalar fields whose continuous Morse-Mel complex can be seen here. It describes a circular shape here, and there's another segment that goes into the bottom left corner. And remember that the discrete Morse-Mel complex aims to describe this using the matchings only. There are many proposals on this method, but the first probably correct methods were introduced by the group of Vanessa Robbins, and we call it steep descent. And this is considered as the standard to extracting Morse-Mel complex nowadays. This algorithm works locally, dividing the grid into substructures called lower stars and working in there. So if, for instance, considering the grid cell here, the values of the vertices of this cell can be seen here. And this algorithm always match the vertex 4 with the edge 4, because it's the steep descent direction. And the rest of the lower star will be matched from there. This results with the Morse-Mel complex, but with the undesirable geometry, as the circular step cannot be seen here. 2 groups work independently to overcome this problem. There's idea also based on the algorithm of the steep descent, so they also work on the lower star. But instead of always moving into the steep descent direction, they assign to the possible choices a weight and chose probabilistically. By doing this, we obtain a Morse-Mel complex with the geometry that is very close to the continuous counterpart. So this algorithm works efficiently to extract the discrete Morse-Mel complex, and the problem of inaccurate geometry has been solved. But the story doesn't end there. By not moving into the steep descent direction, we can produce Morse-Mel complexes which have different topology. For instance, here we use the 2 methods to extract the Morse-Mel complexes on a scalar field interpolated from a randomly generated small matrix. There are 2 separatrices which have different interconnectivity. They are colored red and yellow. The red one on the probabilistic method is connecting to a different maximum, and the yellow one is connecting to a different minimum. They are completely different topology. One can argue that we can overcome this problem using the topological simplification, but that is not the case either. We're considering here a very noisy data set, and we use the 2 algorithms to extract the Morse-Mel complex, and we've simplified them with a very high persistence threshold corresponding to 45% of the data range. And we can see that the problem still persists. The separatrices, the red one, on the steep descent method is missing completely from the probabilistic method, whereas the yellow separatrix is connecting to different minimum right now. The problem gets even worse when we are working with real data set. Considering here a scalar field extracted from a total cloud variable of a time step of the Isabel hurricane data set. And we only shown here the separatrices which have different inconnectivity between the probability method and the steep descent method. And we can see there's a lot of them. And in fact, around 10% of the separatrices have different connectivity. So we've shown that the steep descent method is mathematically proven. It's produced more small complex with consistent topology comparing to the continuous version, but also incorrect geometry as well. The probability chosen methods overcome the problem of incorrect geometry, but in the process of doing so, they also produce different topology of the more small complex. So this leads us to a question whether if we can achieve both consistent topology comparing to the continuous version and correct geometry as well. We've seen that applying the steep descent method on a uniform grid gives us a bad geometry for the more small complex. This is due to the limited choices during the completion of the matching. We either have the vertical or horizontal choice, which are demonstrated through the histogram of the grid iteration here. They are concentrated on very few values, and this gives us a very bad geometry for the more small complex. So a naive idea is to divide its grid cell into two smaller triangles, and we are adding one more direction into the possible choices. And the geometry is a little bit better now. It's a little bit rather for the more small complex here, but it's still far from perfect. So we are moving into the irregular grid, where the vertices of this grid is placed randomly according to the Poisson distribution. And we use Delaunay triangulation to create this grid. Looking at the histogram of the grid iteration, we can see that the values are spread more evenly now. And this gives us the more small complex grid have geometries that is very close to the continuous version. So our idea is that if you want to extract the more small complex, if it's possible, then it's better to have the values placed on the vertices which have a high degree of freedom, for example, irregular grid. But it is not always possible to have that kind of grid in all applications. For most applications, they come with a predefined grid, and most of the time it is uniform grid. So if you want to extract a more small complex on this kind of grid, it gives a bad geometry due to the lack of choices during the computational matching. So our suggestion is to adding more information into the uniform grid. That means we adding one more vertices into the middle of the edges and one more vertices into the cell. The values of the new vertices will be linearly interpolated. And in a sense, we are covering the missing directions, but to a very extent. And this gives us the more small complex with the geometry is very close to the continuous version. In conclusion, we showed that not moving into the steep descent direction can produce more small complexes with different topology, and the differences happens in a lot of scenarios and cannot be removed by means of topological simplification. And we also show that the problem of inaccurate geometry of the steep descent method is due to the limited number of directions during the computation of the matching. So more optimized grid structures can allow the steep descent method to extract more small complex with better geometry. And due to from the observations, we suggest a way to achieve a better more small complex in terms of geometry while retaining the topology from the steep descent method. Our future course is consist of two things. The first one is investigating more on the method that found the category of accurate geometry and better optimize our method to have shorter completion time. That's it for my presentation. Thank you for listening.
Thank you very much, Sean, for this presentation. And we have the opportunity to ask questions. I do not see an initial question. So again, let me start. You have this regular grid, and then you insert new points somewhere in the middle of the cell. Where exactly? Is this random in the middle, or is it exactly in the middle, or how do you choose this point?
For my current implementation, they are basically random points inside the cell.
Mhm.
They can be anywhere, but you can tune them to based on a smaller region, basically.
Okay, what happens if you don't choose it randomly, but just pick the middle, exactly the middle? Is this a good or a bad idea?
No, it's not a really a good idea. I tested it, and it's produced like there's geometry is not that desirable for me, so I just allow it to be a little bit more randomly, and things turned great.
Another question from my side. Can you imagine of a data set or a case where your approach completely goes wrong and miserably fails? Are such cases thinkable?
I'm not sure for my current thing, for my current experiments, like I think more points that's kind of randomly already good enough for most of the cases, but yeah, the problems mostly come from the longer competition time. So yeah, that means if there is a cases where data is really complicated, then anti-more points make it more complicated, and we may be harder to computing stuffs, and that thing may go wrong, I guess. But yeah, interesting question.
Okay. There's another question from Slido. This shows the more small complex extraction highly depends on the mesh configuration. Will the previously introduced MFA address this?
Interesting question. I haven't looked into this MFA, but I will need to look into that. But it's definitely depend on the mesh configuration. But the problem with the circular steps, for example, I showed during the presentation, that is not really depends on the mesh configuration, but there is a possibility that the MFA can address it chance.
The obvious question, what about 3D? What about extension to 3D?
Yeah, I forgot to mention this during my presentation, but my experiments is currently limited to 2D cases. For 3Ds, this will be a little bit more challenges due to the number of possible choices to subdivide the cube into smaller tetrahedron. Yeah.
All right, it seems everything is answered now. So thanks again for the presentation and answering all our questions, Sean.
Thank you very much.
And let's go to the next presentation that is called Multi-Scale Cycle Tracking in Dynamic Planar Graphs. Farhan Rashid, Abra Nasser, Emma Nielsen, Tala bin Masood, and Ingrid Hotz are the authors, and Farhan is going to give the presentation. Let's go.
Yeah, thank you. And hello, everyone. Welcome to my talk. My name is Farhan. I'm a PhD student at Linköping University. Today, I'm going to talk about our recent work, multi-scale cycle tracking in dynamic planar graphs. Okay, this work is motivated by an application in granular materials, and it is collaborated with scientists working with these materials. So the granular materials such as grain, gravel, sands, or etc. are made up of large collection of discrete particles, even though they are made up of solid particles, but their collective behavior is complex and can simply be referred to a liquid, solid, or gases, but with very different characteristics. They are all around us, yet their understanding is so poor. For instance, how they move or behave under external influences is still an open question in science. One direction to get deeper understanding of these materials is through two-dimensional control experiment, where a collection of photoelastic disks are placed in a tray with the moving wall on the two of the sides of it. so that when the wall moves, they put pressure or they put force on the discs, and then these discs with the polarization lights are brightened up and shows these kind of stress pattern. So altogether, when we apply a force on them, they shows collectively a very nice passage of forces in between the systems. So one motivation to do this kind of experiment is to understand the jamming behavior of the system. So what do you mean by what I mean by jamming is that when we push the walls inward, then the disk within the system are starting to sticking together, and at some point they are repulsing the external forces very effectively, and they are no more getting stuck. So lots of disks are getting stuck. So so these kind of patterns are captured by a camera on top of this this setup, and after extensive pre-processing or with image processing and optimization method, the underlying contact network here, which is extracted. So this resulting force network is dynamic because you can extract for each moving walls, for each loading conditions, for instance, and this work is about the analysis of this force network in order to understand the granular material better. It is established for solid, liquid, and gases that the macroscopic properties can be simply derived from the microscopic property. However, in the case of granular material, the macroscopic properties, such as mechanical property or the stiffness or the hardness of the system, cannot be simply derived from the microscopic properties, such as the position of the disks, or the velocities, or the rotation of the contact information. So to overcome this issue, scientists have suggested to introduce an intermediate scale called mesoscale, and analysis of granular material through intermediate scale, which will bridge the gap between macro scale and the micro scale and will help to aggregate the property from the micro scale to the macro scale, is an active research topic in the science. So in this work, we focus. So the structure in the mesoscales could be a cluster of particles. So in this work, we look at the cycles within these networks. So these cycles are interesting because they confined the particles that you can see in the below here. They are not directly participating to the force transmission in the system. They are not part of the force network, but still these are color-coded by pink, and we call them loose particles. So these particles are really contributing or to understand the stability of the systems. So this work is the extension of our previous work, where we have proposed an approach to extract the cycle from our force network at multiple scales. So here is an overview of our previous method, where we are extracting the cycles at multiple scales. Let's say our force network is denoted by a graph G with vertices V, which are the center point of the disks, and the edges, which defines the contact between 2 points, and the weight, which is a measure of the force value. So we compute the full partitioning of the domain such that the boundary of one segment in our partitioning will be the cycle in our original graph. How we did that? We compute a constrained Delaunay triangulation such that our input graph will be part of our constrained Delaunay triangulation. From this Delaunay triangulation, we have computed the dual graph by combining triangles which are connected with the non-force network edge. So this here, the below graph here is our dual graph, and using Alexander duality theorem, this duality exists like that the connected components or the homology group 0 in the dual graph will be equivalent to the cycles in our original graph. So in summary, we explored the Alexander duality theorem, which is basically instead of working on our original graph, we have worked with the dual graph, and we will get a nice representation of the cycle in the case of full partitioning. Since our Delaunay triangulation is made up of our force network and using a edge weight filtration, we can get the hierarchy of our partitioning. So which can simply be represented by a hierarchy tree, which is similar to the merge tree. So far, we have worked with single instance of our dynamic force network. However, in practice, we get a time series of force network resulting from a single experiment. For example, moving the wall inward or outward at each value of or each position of the wall, we can get another force network. And so we can get another Delaunay triangulations. So one thing here to note that the underlying Delaunay of this partitioning is changing. For instance, you can imagine that if you move a wall inward, then the position of the discs are going to change. And when you're going to compute the Delaunay triangulation, which also change. So here we are technically the challenge with the underlying geometry is changing. The goal of our this current work is that we are tracking these partitioning or the cycles over time and scale. So then the second goal is to efficiently layouting our resulting tracking, which summarizes the entire experiment. And we provide a good or efficient color map so that we can provide with a good spatial context. There have been previous work in multi-scale tracking based on merge tree developed for scalar fields. However, here we are tracking the cycles within a force network, or we can say that within a changing geometry. So the underlying geometry is changing. Here is an overview of our proposed method for computing the correspondence between adjacent time points. Given a Delaunay triangulation for two adjacent time points, we can compute the hierarchical information of the hierarchy of partitioning. We compute an overlap matrix A with rows M and N, where M are the number of triangles in Delaunay triangulation dt, and N is the number of columns, which are the number of triangles in the Delaunay triangulation dt plus 1. So in short, we compute the correspondence between all pair of triangulation. So here entries of this matrix is the measure of overlap between two triangles. So the matrix at the end, when we compute the overlap for each pair of triangles, the matrix is sparse at most, because most of the triangles does not really overlaps. The benefit of computing this overlap matrix is that based on this matrix, we can compute the correspondence between the cycles at any level of tree by exploiting the hierarchical information. For instance, if we have two triangulations that are overlapping, then their parents will also be overlapping. So we provide a way, we provide the option to choose the same threshold based on their same threshold for the tree, or based on their relative percentile. We repeat the process for all adjacent time points and get a tracking graph information like that, where nodes are the cycles and the links represented the correspondence. Having this correspondence information in place, we can lay out the graph using Sankey diagram. So by projecting each individual time point on a one-dimensional axis, we facilitate the insight of the single time point. The vertical position is inferred from the connectivity information. We connect the nodes in adjacent time points by link whose width is proportional to the measure of the overlap. So since this is the tracking of the full partitioning, the resulting tracking graph has high link to node ratio, which means that keeping track of individual cycle or the individual segment in the partitioning is non-trivial. Therefore, we propose to color the nodes and link using a two-dimensional color map. This emphasizes the location of the cycles and help us to show how nearby cycles are developing throughout the domain. Now come back to our original question where we want to understand the jamming of our granular system. We apply our method on one of the loading and unloading experiment. Loading means when we are moving the walls inward, and the unloading when we are moving the walls outward. So during loading, the load is applied, and the interest here is to understand the development of the jamming in the system. So here is the result of this experiment. Our visualization provides good insight into the jamming behavior. As we can see from left to right, when we slightly move the wall inward, there's no much things going on. We can see there are some development of the cycle. They are splitting and merging. But at point 8 and 9, the cycles, the big cycle which were carried on before is split into lots of small cycles, mostly in green, yellow, and this blue part. So which means that on this part, if you can see from the contextual image down here, we can see that these area or these part of our domain are jammed, more jammed than the other ones. If you can see these orange part and the violet part and the red part, they are kind of stay same throughout the jamming, which means that the disk enclosed in these cycles remain loose throughout the experiment. So finally, at the end, when we move the wall outwards, so the cycles are again combining together and combine to one single big components, and so on. It goes like that. Okay, that was it. So in summary, we provide a method to track cycles in dynamic planar graph that has the dynamic geometry. We computed at a multiple scale and visualize the tracking graph using Sankey diagram. And with the 2D color map, we get a good contextual understanding, and we get the insight into the jamming effect of the granular materials. With that, I would like to thanks.
Thank you very much for the presentation. We have time for probably one short question. I don't see any questions on Slido. Let me start. The examples you have shown are approximately of the size, I don't know, 25 times 25 particles, something like this. Was this the most complex data set where you applied your algorithm, or how does it scale to more complex data sets? So
these are kind of around 1,000 disks in one experiment included. So what they really want to understand understand this granular material through this scale, like the very small scale, and they wanted to kind of extrapolate to the higher level. So the experiments are done typically within these range of the particles. So we get the underlying network out of these.
Okay. Another question Baywan is asking, does the tracking automatically reveal the start of jamming or overloading?
Yeah, so this is the thing can be explored by the domain scientist, but here you can see the upper row where the below time points are where the domain scientists have kind of noted out, okay, this until 7 there is no jamming, from time point 8 to 13 there is a jamming going on. So this is the only information they get by looking at the one thing called packing fraction, like with their own typical methods. But for our method, we can get the more insights into the jamming behavior. So we can see, okay, which part are jamming, like directly looking at this red bar here, red link here, that remains the same throughout the jamming. So we can say that, okay, So wherever we're putting the pressure or the external forces, some parts stays like that. Some disks are entirely does not really contribute to the system.
All right. Then thanks again for the presentation and answering all the questions. And we come straight to the fifth and last presentation that is called Asymptotic Topology of 3D Linear Symmetric Tensor Fields. The authors are Xingwei Ling, Yue Zhang, and Eugene Zhang. And Yue is going to give the presentation. And here we are and ready to go.
All right, Holger, thank you for the introduction. I am here. I'm not a robot, but my camera kind of disappeared this morning at the beginning of the conference. So I'm going to compensate with some busy slides. Bear with me. So this is a collaborative work with Xingwei Ling, who has graduated and found job in the communications industry. And Professor Eugene Zhang has been leading this line of work in our paper. My talk is on the asymptotic topology for these 3D linear symmetric tensor fields. We're interested in applications in solid mechanics and fluid dynamics. So on this slide on the left, you can see a very simple mechanical loading problem, a block made of polymer, and we're pushing down on one side, pulling up on the other side. Then the question is, what's inside the block? What's happening there? The right shows our tensor field analysis. On the left, you see these orange color surfaces and yellow curves. On the right, it's different cyan surfaces and green curves. These are topological features. The yellow curves are the planar degenerate curves. The green curves are the linear degenerate curves. The orange surfaces are negative mode surfaces, and the cyan surfaces are the positive mode surfaces. So interestingly, the curves actually have the largest mode values. The planar yellow degenerate curves are at -1, the linear and green curves at +1, and the surfaces have mode values in between. We also include neutral surfaces. These are what we see here on the right of the screen, the chartreuse color surface or apple green. These surfaces have mode value 0. What about other surfaces? What are their mode values? In this image here, we see that these other surfaces have mode value between -1 and 1. So we're interested in knowing what are the interactions among all these mode surfaces, including the degenerate curves and the neutral surface. We notice that when these surfaces are close to the degenerate curves, we're looking at these yellow and green curves. They look like they are kind of straight. And when these surfaces are close to these curves, they enclose them. That's why we see these cones. But when they are close to the chartreuse color or apple green color neutral surface, they kind of converge onto this neutral surface. So this is just showing the transition from enclosing the degenerate curves and then opening up and converge onto the neutral surface. This transition to us is meaningful. And we also note that these surfaces and degenerate curves, they seem to straighten up. They have some complex structures near the center, but they seem to straighten up when we extend to infinity. And this is the motivation behind this work here. What is the asymptotic behavior of all these mode surfaces? Neutral surfaces, degenerate curves, and other mode surfaces have values between -1 and 1. A very quick review of subset of work that are pertinent to this paper here. The degenerate points were introduced in 1997, and in 2004, it was proven that these points actually form curves. And in 2016, the neutral surface was introduced and included in the tensor field topology study. In 2019 and 2016, there are papers published to have fast and robust extractions of these features. Last year, there was a paper that introduced a graph visualization to show the global topology of these 3D topological features and their interactions. Our work, to our knowledge, is the first to study this asymptotic behavior of these linear symmetric tensor fields. So briefly, what is the tensor field that we're looking at? It has this linear form, and we continue. Please notice the x, y, z. These are points in 3D. And we continue to focus on this subset that's symmetric, and they're the deviatoric part, meaning the traceless part of the tensor fields. So there's a difficulty because when we look at this asymptotic behavior, it becomes infinity because we want to look at points where x, y, z are at infinity. So our strategy is to normalize. Now we're looking at t prime, which is normalized and has a magnitude of 1. We also note that this t prime is path dependent. Thus, we invoke parameterization. Here is in terms of tau to parameterize the path. The main contribution of this paper is that we create this sphere of infinity here denoted by S sub infinity. On this sphere of infinity, we can see that the degenerate curves are actually show up as dots. Here we see the dots for the degenerate curves, and then a loop for the neutral surface. We also note that there's antipodal symmetry. In other words, the S positive is congruent to the S negative. And these were the dots and loop that I was talking about earlier. Now, the question is, how are these features interact? How do they interact on the sphere of infinity? From our past work, we know that there are at most 2 or 4 degenerate curves for these linear tensor fields. Thus, on the sphere of infinity, which is on the right, we would see 4 or 8 points on the surface. And for neutral surfaces, we would see 1 loop like this one here, or 3 loops like this one. 1 loop, if you notice the image on the left, it has a finite handle. It may be a little bit hard to see. For this one, 3 loops, it's infinite handle. The 2 cones would connect in the infinity. And because of these intersections, the sphere of infinity would be divided into 2 disks, or sometimes 2 disks and 2 bands. These are the 4 total cases that we have discovered. The next question is, how many loops? What are the results for an arbitrary mode value, or mu? So we know that when the mu is close to plus minus 1, so the degenerate curves, they enclose these degenerate curves. And the counting is double. So that it's a number of degenerate points. But for the neutral surface, because the surfaces converge onto the neutral surface from both sides, it's also doubled. Then what about the other values? Okay, other mode values. We note that under structurally stable conditions, this mode function is Morse. That means all critical points are isolated. So this translates our problem to study the number of critical points for this mode function. And next, I enumerate what we have found, the different cases for this different values of mu. For different values, we can find different pairs of critical points on this sphere of infinity. There can be 3, meaning the red dots and the blue dots we see here on the surface. 5 pairs, some more pairs. So on the left is the front face of the sphere, the right is the back face. And 7 pairs. It's either 3, 5, or 7. And each time it's a pair. The proof is a bit complex, a bit involved, and it's included in our paper. So to enumerate the 6 cases that I just talked about, when we have 2 degenerate curves, there can be 3 critical point pairs or 5 critical point pairs. When we have the 5 critical point pairs, there could be a pair of local extrema. And when we have 4 degenerate curves, we only have 7 pair of critical points. And I'll show some visuals here. So this is the first case. We have 2 degenerate curves. That's why we see 2 yellow dots. And encircling each degenerate point, these dots, we have 2 loops. And we have the neutral loop that's separating the cyan color and the orange color. And we can see that when we vary the mode values from A to D, these loops interact. This is the second case where actually there's a loop that can self-collide and split. I have some red arrows to help guide your vision, your attention to those places. And this is another case where these 2 loops actually a third loop could appear and interact with the existing loops. And at the end, these loops would converge to the neutral loop. Again, from A to D, we're just dialing up the mode value. And this is another case where a third loop is appeared, and again interaction with the existing loops. And now we go to the 4 degenerate curves, and that's why there are 4 distinct loops at the beginning. Again, these loops they merge and they interact at the saddle point, saddle pairs. This is another example, second example for the 4 degenerate curves. In this case, the 2 loops actually split. These images are just for us to get the idea that these loops actually interact on the sphere of infinity. The observations that we have made are that include that the S plus and S, the positive and negative halves of the sphere of portions of the spheres of infinity, they can consist of disk and bend, and the loops do not disappear on their own. They merge or split at the saddle point. This is a table that summarizes all the cases that I have discussed. The last column shows the sequence of interaction, merging, disappearing that we have observed for the 6 cases. You can see that 4 loops at the beginning can become 2 loops at the end, and the last case with 8 loops at the beginning but go through different number change when we end at the last mode value. The conclusions that there are a total of 2 loops, at least 2 loops, and at most 8 loops on the sphere of infinity. And this is a summary. Due to time constraint, I won't go into details, but now we have achieved defining some interactions of the asymptotic topology for the tensor fields, for the linear symmetric tensor fields. For future work, we'll provide more rigorous mathematics proofs for all the observations. This time we'll report some proofs and some observations. We want to connect more to the physics side and have more demonstrations with the application topics. This work is we thank the anonymous reviewers on this work, and we also had past students who contributed to fruitful discussions while they were studying in our group. Thank you for your attention.
Thank you very much for the presentation, Joey. In the interest of time, we have time for just one question, and this question is already in Slido. These are really intricate structures. Are there any physical implications associated with them?
So my quick answer is definitely yes, because if we don't study these tensor field visualization, we would not see these structures, surfaces, and linear degenerate curves. So what are these interactions? It's mostly between extension and shearing. Excuse me.
All right. Last question, short answer. Can you build upon this for asymmetric tensor fields as well?
Yes. Yes,
that was the shortest.
Yes,
that was the shortest answer I was expecting. Yes. All right. So thank you very much. This is the end of the session. So let's thank all the speakers again for the presentations. And with this, I think I give the word back to Federico for the poster presentation.
That's right. Thank you so much, Holger. And yeah, last but not least, we have our poster presentation session. Like now, this session was supposed to be sort of a lighting talks to kind of ignite then the official poster session that would have happened afterwards with the general IEEE's poster session. So just one recommendation for all of you, please engage with our presenter later on, either today or in the next following days. Like they will surely be very happy to chat with you about their work. Now, without further ado, we can already jump into our first lighting talk associated with one of our poster, which is like the talk title is Exploring a Relative Geometric Position of Isosurfaces in Multi-Fields. And our speaker is Akito Fuji. Akito, are you there? You can already share your screen if you want.
Yep. Okay. Yes. Can you see my screen and can you hear my voice?
We can see your screen and your voice as well. Like we probably see there is part of the user interface of Zoom on your side, but it's probably like but pops on our side too. Yeah, I see you got rid of some of it. Fantastic. So Akito, the floor is yours.
Yes. Okay. Okay, hello everyone. My name is Akito Fuji from Kyushu University in Japan. Today I will introduce about exploring relative geometric positions of isosurfaces in multi-field. Yes, the main idea in our research is a new feature extraction. We have focused on relative positioning of contours in multiple fields. For example, look at these pictures. Each picture represents a contour map in the same domain, North America. This is a pressure map, and the other is a temperature map. A white contour in a pressure map represents low pressure or high pressure region, and black contours show low temperature or high temperature region in the temperature map. We want to analyze correlations, especially relative positioning between pressure contours and temperature contours like this. In this picture, we want to understand relative positioning between white and black contours. However, as you can see, there are numerous pairs of black and white contours in order to analyze relative positions. This is a problem for us. Thus, we propose new correlation analysis methods. our proposal is a phase diagram of relative contour positioning for contour combinations like this figure. This is a sample image. This rectangle represents the set of pressure and temperature contour pairs continuously. We assign semantics about relative positioning to contour combinations in this rectangle. For example, in this rectangle, a pair of contours in pink region, for example, has the semantics about low pressure region lies west to low temperature region. For example, this one and this one's correlation in this picture. On the other hand, in the green regions, pair of contour has the semantics that the low pressure region lies east to low temperature region. So, for example, this one and this one has this correlation. We call this rectangle with semantics as a phase diagram. Technically, this rectangle consists of two edges of contour trees. In this example, this rectangle consists of an edges of contour tree of pressure map and temperature map. By using contour trees for all contour combinations in this picture, for example, we can assign semantics like this relative contour positioning. Yeah, we believe that the phase diagram helps us analyze correlations between two scalar pairs like this relative positioning. Yeah, so thank you for your attention.
Great, thank you so much. And I'll jump in with a quick question. If anybody wants to ask questions right now, please post them here on the Zoom channel, since I'm not sure we have the student volunteer copying the question from Slido right now. My question is, well, like, if I'm curious if you guys like have already looked into, real data and real data with noise. And so I'm particularly curious to see if you did that, like what the impact of noise in the original data can be on the diagram and that you're proposing.
Yes, this is a nice question. Maybe with in the real data, yeah, this has many noises. So if we compute this diagram in the real field, real data, then first we simplify the data structures like contour tree. Then by doing so, maybe we can remove some noises in the real data. So maybe we can extract the central character of the topology of the contour relationships.
Sounds great. Sounds great. And we have another question here in the chat. Actually, two questions. Have you considered the temperature and humidity pair rather than temperature and pressure? And as a follow-up, have you considered like these analyses over time, over a year, for example?
Sorry, one more, please. Sorry, one more, please.
Should I repeat that?
Yeah, sorry. Yeah.
I can do that. The question is, it's also here in the Zoom chat if you want to read it. But like the first question is, have you considered the temperature and humidity pair?
Temperature and humidity.
It's something that you guys have explored already?
Yes. We considered. So we have considered about the humidity and temperature. But in this slides, we introduce the pair of the pressure and temperature, but in the experiment or analysis as a pair of the physical object, yeah, we can consider it.
Sounds good. And the other question was about the time aspect. Like, have you guys considered like analyzing this data over 1 year period, for example? Would this be doable?
Oh, speed, yeah. Yeah, maybe yes. Maybe this research is over this year, maybe. Yeah, maybe
Sounds
this year. Yeah. Yes.
Sounds good. Thank you so much. Let's thank
Yep.
our speaker
Thank you.
again, and let's jump to the next lightning talk, which title is Sublevel Set Persistent Homology for Distance-Based Classification of One-Dimensional Time Series. And our speaker is Caleb Lees.
Hello there. Can everybody hear me and see my slides?
Yep.
Okay, fantastic. Thank you. So thank you for the introduction. My name is Caleb Lees. I'm a mathematician for the Air Force Research Laboratory up in Dayton, Ohio. And today I'm just going to give a very brief overview of the poster that my team and I submitted to this workshop. So the aim of our research here is exploring the classification of one-dimensional time series using sublevel set persistence diagrams. And there's some motivation for this particular direction. In particular, distance-based time series classification offers a balance between computational simplicity and competitive classification performance. And more recently, as TDA has kind of developed as a field, time delay embedding simplicial complex persistence has been shown to achieve promising classification performance in this particular area. However, our team is concerned with sublevel set persistence as opposed to simplicial complex persistence, as it is generally more approachable from a mathematics perspective and is computationally faster in almost every situation. So I'm going to assume that the majority, if not all, in my audience are familiar with sublevel set persistence of one-dimensional functions, but if not, I'm happy to entertain questions to that end later. So here's what we did. We selected 11 time series data sets from the UCR time series archive. These are all pre-labeled, z-normalized, and they vary in size, length, and number of classes. So we have some diversity there. And then our aim is to compare a bunch of different distance metrics, including our sublevel set filtration distance, which I'll explain in a second. So two of them are non-topological in the sense that they do not compute persistence diagrams. These being the Euclidean distance and dynamic time warping, both of which are very established in the literature of time series classification. Two of them are topological, and these are the sublevel set approach, whereby we compute sublevel set persistence diagrams of each one-dimensional time series, and then we compare them using the Wasserstein distance. And then we have the analogous approach for a simplicial complex filtration, whereby we compute a time delay embedding of the persistence or of the time series, and then compute a persistence diagram and compare them using the Wasserstein distance. And then two more metrics that we're interested in are mixed non-topological and topological distances. And these are achieved via the topological geometric mixed distance of Zhang et al., a nice paper written in 2021. So for example, the SLS plus DCW distance is basically the dynamic time warping distance augmented by topological features that sublevel set filtrations pick out in the time series. And the similar thing for the simplicial complex for plus dynamic time warping. So those are our metrics. The classifier that we chose to use was one nearest neighbor, basically because it's very easy to implement, and it's been shown that its performance relies directly on the distance metric that is used. So it's appropriate in our setting, I believe. And then finally, we evaluated the classification performance of our metrics using weighted F1 scores. So here are those F1 scores in tabular form. And since I don't have a whole lot of time here, there's really only two things I want to point out. The first thing is that the sublevel set filtration distance generally is vastly outperformed by non-topological methods, namely the Euclidean distance and dynamic time warping. And this really is not that surprising because sublevel set persistence diagrams kind of lose a lot of information, namely kind of temporal positions of relative extrema. That's kind of a big thing that it loses. So there's kind of some symmetry in the time series that is lost when you compute persistence diagrams. However, something that we found, and I think a direction that we can go in the future, is that if we use the topological geometric mixed distance that I mentioned on the previous slide to augment dynamic time warping using these sub-level set filtrations, we actually achieve a distance metric that outranks everything else that we tested using the average rank statistic. And so given that this is a very rudimentary test, we kind of have some hope here that maybe this can be extended to more distance metrics. Maybe the sub-level set metric can augment other distance metrics. So that's kind of a direction that we want to go. And hopefully we can test this on a larger number of time series and add some noise to our time series and see how robust this method is to noise. And so there's lots of different directions we can go here. So in the interest of time, that's really all I have to share, but I'm happy to entertain questions. Thank you very much.
Thank you so much, Caleb. I'm already going to jump in one of the questions that I see in the chat, which is there are many DTW variants. Have you considered multiple of those, or you pick the one that you prefer for a reason?
So yes, you're correct. There are many DTW variants. We just chose one that we found in an open source repository, just so that we have a baseline, kind of measure for dynamic time warping. And yes, it would be interesting to look into other dynamic time warping algorithms, as they can produce some different results in classification performance. So yeah, that's a good direction to potentially go in the future. Thank you.
And a very short question from myself. I'm curious, how confident are you that this is a promising direction and not maybe a specific problem of a data set that you pick? I guess the question is, how about generality? Can we really hope to find this resulting on other data set, or?
Yeah, so this is a fantastic question. The confidence level is fairly high that we can extend this in a way that's meaningful. And the reason for that is that we were able to identify some specific cases in which the sub-level set filtration actually outperforms dynamic time warping, in particular when it's able to kind of pick out different heights in relative extrema that dynamic time warping cannot. And so one direction that maybe would be promising is looking at particular data sets where the height of relative extrema in your time series is relevant. And so the theory there is that maybe that our method can outperform dynamic time warping by augmenting it. So yes, there is hope, and I have fairly high confidence that it can be reproduced in other examples.
That's fantastic. Thank you so much for your answer. And I want to thank all our speakers once again of these lightning talks. As I said, I really encourage all our attendees to engage with them during the rest of the conference. And with this, well, to engage online. And with this, we're going to conclude the poster presentation session. I'm going to take it back to Guoning for our concluding remarks.
Sorry about that. I lost my interface, so I could not unmute. So, okay. Thank you, Holger and Federico, for hosting the paper session and the poster sessions. So thank you all for joining us today for the workshop. I know we were up for a bumpy start, and we made a call to switch to the, Zoom link that actually I think it's more engaging than we just, did it in the conference Zoom. And again, congratulations for all the papers presented today, and especially for the best paper. And Federico, congratulations. And you've received follow-up instructions for how to actually submit the extended version to TVCG. And again, I want to thank the organizing team for this workshop. Without your support and effort, this will not be happening. Again, I just repeat myself, thank all the support I received from the IEEE's core organization team, especially the tech team. Even though there is some, technical complication today, we still thankful for the support we receive. Thank you for Peter. If you're still around here, it's a big shout out. Thank you for, staying with us. We have this, technical, glitch, and I humbly requested you to repeat some of the content, which is sorry about that. And then, yeah, again, congratulations to all the authors, and then our, IPC, all the members made their effort to review the submissions, and the efforts, made by the Best Paper Award Committee. And then again, Session Chair Holger and Federico, thank you for, moderating all the talks to make sure we, get it done on time. Yeah, we are about to get it done on time at the central time, about 3 p.m. But we'll get it done. We'll get it done. And yeah, for the best part, thank you for staying with us, especially people on the other side of the earth. Appreciate that. And then now talk to about farewell. And then me and Federico are stepping down. This is our second term, so we're looking for new people to join the organizing committee. So we need one person to fill in the overall chair and one person for paper chair. And then you get the support from Divya and Yuet, and I hope you enjoy working with them. And if you're interested in, please email the steering committee at this email address to nominate. If you know somebody that are good for these jobs, please also nominate them. But of course, first get their agreement to do that before you nominate them. And last but not the least, please enjoy the rest of the IEEE. And then we see you all in the next iteration of TopoInVis workshops. Hopefully we get to see you in Vietnam. But before you sign off, this is a short survey. Please help us fill it up. It will help the next chair to make a pitch to the IEEE and also help us make a community. If we want to announce any events and things that we want to get attention from you guys, this will help. So please take some time to fill up the survey. And that's all. Thank you very much.